And good morning, everyone. I'm Sunil Kumar Singh, and my title is an HSDT-based xiga approach for vibration analysis of cracked bidirectional functionally graded plate. So this is part of my PhD student research work. So this HSDT is higher order shear deformation theory. This is plate theory. Likewise, we have the several plate theory, CLT, classical laminate plate theory, first order, FSDT, and HSDT. So my outline of presentation is first I would discuss this background, followed by the motivation, then objectives, then methodology, since I used only the formulation, and later on I make this formulation in code and I write my in-house code in MATLAB of this extended isogeometric analysis. It is a numerical technique to simulate fracture problem in different material. Then result and discussion and conclusion. So why we are using this FGM? So as we know, in nature, we already have this FGM, that is functionally graded material. So if we take the example of this bamboo, so here the fiber is denser, and this, as we move from the outer radius, the fiber, the density of the fiber is decreasing. Likewise, we have another example that is the natural functionally graded material is bone. So if we see this outer portion, that is the cortical bone, is highly stiff, and the middle portion, it is highly porous and soft. The main purpose of this stiff outer portion to stiff is to it resist the compression, and the middle portion or the portion which is highly porous, its purpose is to absorb the shock. Now, the man-made FGM was first developed by this Japanese researcher in year 1984 with an aim to, if we take the example of the composite material, so the material properties is varying constant, but functionally graded as name suggests, so we are using some function, and gradation in the domain can be done with the help of the function, and we are getting the continuous effective properties. So FGM is widely used in the engineering practices ranging from nuclear, aerospace, electronic, and many more. Now, all these, mostly the research has been done on the unidirectional functionally graded material in which the properties is varied along the one direction. Now, if we take the more practical example, likewise, like we have seen the natural example, that is the bone. So this bidirectional FGM is, you can say, is more realistic. So how we are defining this bidirectional? So I have taken a simple illustration. So of plate, it is a three-dimensional body, and we have three material. Here. This is 100% material 1 and material 2, and it is material 3. So material properties is varying in x direction from material 1 to material 2, and it is varying from material 1 to material 3 in the thickness direction. So how we are varying this material properties using some function, and that function is the power law function. So the constituent material here, the constituent material is three different constituent material we have. So this is the plot showing how this constituent volume fraction is changing over the domain. So this x by a is showing longitudinal, and this z by h is the thickness direction, and this plot shows how the volume fraction for the material 1 is changing, V1. Similarly, this is for the expression for the V2 and the plot, and for this V3. Now, for my work, since this work is computational, so I have taken these material properties. Material 1 having 110 gigapascal, and I have taken the Poisson's ratio as constant. And the density of the material is also different. And we know this, the effective material properties and the effective density can be obtained using the rule of mixture. So this E1, E2, and E3, let's say we have the Young's modulus. So this E1 is the Young's modulus of the material 1, E2 is the Young's modulus of material 2, and 3, like that. Similarly for the density. And these are the plot. And here we see in the previous slide, this N and Q is defined. Since we are writing the effective properties in terms of volume fraction, and we have this N and Q. We have this N and Q. So these are the, you can say, gradient index here we have. So if we change N and Q, the material properties along the thickness and along the, you can say, longitudinal direction will change. So I have taken two value. This N is equal to 2 and Q is equal to 5. And this is the plot for the effective Young's modulus, and this is for the effective density. And it is normalized over the material by the material properties, Young's modulus of the material one. And for this N is equal to 0.5 and Q is equal to 0.5. So you can easily visualize this, how this material properties is varying from here to here. This from here to here, it is varying in this way. Here it is varying using some different function. Here it is varying using different function. So we have the choice to change the material properties by taking this N and Q. And one more thing, if we take this N is equal to 0, then it become unidirectional functionally graded material. So the material properties only varies in the thickness direction. So now this bidirectional FGM is mostly used in the aerospace engineering for making the fuselage. And as we know, this fuselage is composed of several plate type of structures. So why we are studying this fracture? So we know in the history of technology, we have the several failure, catastrophic failure, which led the designer and researcher to rethink over the different design philosophy. So we have the different approaches to solve the fracture mechanics problem, ranging from experimental to numerical. So as of now, as we know, we have a vast computational resources these days. So nowadays, computational technique is preferred over the experimental. I'm not saying in that way, but computational technique is preferred because it requires less resources and it is less expensive. So my objective is to develop the xiga formulation. Xiga is extended isogeometric analysis. So as we know, we have the finite element analysis where we are using this Lagrangian shape function. So this isogeometric analysis uses the CAD basis function. The common CAD basis function is the NURBS basis function. That is the non-uniform rational B-spline basis function you are using. So first, I developed the formulation for the vibration analysis for this plate. And I use this higher order and well-known this Reddy's HSDT theory I have taken. And then I incorporate this enrichment function to model the crack. Then we have developed a code, an in-house code for the vibration analysis to perform the vibration analysis of this bidirectional FGM plate with crack. Then the natural frequencies is computed having different parameter. That is the volume fraction coefficient. We know with in the volume fraction coefficient, we have these N and Q. Next, this aspect ratio. Aspect ratio is the side length of the plate. And then crack length ratio. And we have the different, obviously, the different boundary condition. Now, the thing is why we are using this isogeometric analysis over the finite element method. So here the simple illustration shows. So let's say we have this curved domain, we want to mesh it using finite element. So you see how many nodes and how many elements are required. And even though this curved boundary is not captured accurately. However, if we take this isogeometric analysis where we have the CAD basis function, the NURBS basis function, only we have the two element in this direction. Here in the radial direction, and here it 2. So we can say the discretization error can be eradicated or can be controlled when we use this NURBS basis function. One more thing is the Lagrangian basis function. Since FEM uses Lagrangian basis function, and Lagrangian basis function is always C0 continuity, has a C0 continuity at the junction of the element. So like plate structure where we are using the higher order shear deformation theory and the bending is more dominated, so this finite element will not capture this Lagrangian basis, we have to take some different basis also for the different degrees of freedom. So one of the advantages is higher order continuity can be achieved in this nerves basis function. And one more thing is the refinement technique. We have in FEM, either we do the H refinement or P refinement. Means we can increase the node or we can increase the degree of the polynomial, Lagrangian polynomial. However, we have here K refinement in isogeometric analysis. This K refinement, together we can do the degree elevation as well as the knot insertion. Knot insertion is something like generation of the node. And moving on to this, for simulating the fracture problem, we use this extended isogeometric analysis. Likewise, it is extended, likewise, same to this extended finite element method. So in order to model the crack, we require, so this is the, let's say we have this crack in the domain. So these are the control point corresponding. So we have the crack face and crack tip. So corresponding to the crack face, we have the different functions. So we know the crack is discontinuous, the displacement is discontinuous. And at the crack tip, the stresses is singular. So in order to capture this singularity behavior, we use different function. And in order to capture the discontinuity in the displacement field or primary variable, we use different function. So the approximation function is modified using this enrichment term. And this enrichment term is of two types. This is Heaviside function, and this is asymptotic crack tip enrichment function. So we know when we have the displacement discontinuity means one side of the crack takes positive value and one side of the crack take negative value. So we know this Heaviside function is similar to that. So this Heaviside function, if we take positive value, then its value is +1. And if we take this negative, x is negative, then it takes -1. And this is the asymptotic crack tip enrichment function. And this is different for the different material. If we take this plate bending problem, we have also the different enrichment function. This is the normal plots for the 2D nerves basis function and how we are enriching this. So you can easily see how this discontinuity is captured. And this is the asymptotic crack tip enrichment function. So I have developed my this in-house code. So first, this validation study. So I have taken a plate subjected to bending load, or you can say not bending load, sorry. This is vibration analysis. So it is free by vibration analysis. So it's vibrate by its own weight. So this boundary condition is SSS. So it indicates all edges are simply supported. And I have taken this B by H is equal to 50 and D by B is equal to 0.3. So the result is validated by the paper Huang and all in this 2012. And I have taken this material properties. So as I said earlier, this N is equal to 0.2 and Q is equal to 0. So there is no any result available for the bidirectional. So I have validated my code by taking this value Q is equal to 0 over the different mesh sizes or control point. And I come to know I can take this 28 cross 28 node where the result is converged. And these are the different mode shapes I am getting. Now for the bidirectional, this is the parametric study. I have taken this D by B is equal to 0.3 and B by H I am varying from 5, 20, 50 and 100. These material property is same, and we have taken these two cases. N is equal to 2 and Q is equal to 2, and this case 2 is N is equal to 2 and Q is equal to 5. For the different cases, for case 1 and case 2, I have obtained the natural frequency for the lowest 5 mode shapes, model frequency, natural frequency. Okay. So this, you see this B by H is equal to 520. So as we move on as we increase this B by H ratio, the natural frequency got increases. This is the reason. So we know this natural frequency is related to the stiffness, and so this increases. Now these are the different mode shapes we have. Now for B by H is equal to, I want to see the effect of the crack crack length. So as we increase the crack length, the more natural frequencies decreases. And this is the plot for the, when we orient the crack for the different angle. So we see the at 45-degree, the frequency is less, and it is maximum at 0-degree and 90-degree. And these are the different mode shapes for different orientation of the crack at theta is equal to 0 and 60-degree. So I can conclude this higher order continuity requirement of HSDT, since higher order HSDT requires even continuity, which can be easily satisfied by this in the extended isogeometric analysis. The natural frequencies B by H varies in this way. So B by H greater than 100. For thinner plate, the natural frequency is more. And also the boundary condition, effect of boundary condition, the clamped boundary condition provide stiffer, you can say more stiff. So obviously the natural frequency increases, and normalized natural frequency decreases with the increase in the crack length. I would like to thank this Anusandhan National Research Foundation for providing me the financial support to attend this conference. And I also like to thank my institute, Indian Institute of Technology, for providing financial support for this work. Thank you.